Ben Green was born in 1977 in Bristol, England. He was educated at Trinity College, Cambridge, first as an undergraduate and later as a research student of Timothy Gowers. Since 2001, he has been a fellow of Trinity College, and in that time he's visited Princeton, the Rennie Institute at Budapest, the Pacific Institute of Mathematics at UBC, Vancouver, and he was a fellow at the Pacific Institute of Mathematics. In January of 2005, Ben will take up a chair in pure mathematics at the University of Bristol, and he will speak to us today about primes, past, present, and future. Thanks, Ben.
Well, thank you very much for the invitation to come to Harvard. Someone once told me that there are two types of number theorists, those who multiply primes and those who add primes. Don't know quite what they were implying by that, but I'm one of the latter type. And I guess the first person to really start adding primes together was Goldbach, Christian Goldbach, who wrote a letter to Euler about 250 years ago. And he just asked the question, is every even integer a sum of two primes? And to this day, nobody knows the answer to that. But there has been some progress. A mere 187 years after that, Vinogradov proved that every large odd number is the sum of three primes. And what I'd like to talk about today is, so this is a linear equation in primes, which is the title of my talk. And what I'd like to talk about is largely a particular type of linear equation in primes, or system of linear equation in primes, which are arithmetic progressions. So, probably most people know what an arithmetic progression of primes is, but let's just start off simply and write down some examples. So 3, 5, and 7 equally 6 and all primes. And same with 5, 11, and 17. And the reason these are related to linear equations like this is that these satisfy the relation P1 plus P3 is twice P2. So what's known about linear equations in primes? I'm not doing very well at keeping the audience's suspense with this thin paper, am I? So there's Vinogradov's result that I mentioned. Is it still? I think that's much better. Yes, so in 1939, pretty much using Vinogradov's method, van der Korput showed that there are infinitely many triples like 3, 5, 7, and 5, 11, 17. And in fact, not much more has been done since then as a result of Heath-Brown. From 1981, which can be described as saying that there are infinitely many 3.5 term progressions of primes. So let me say Q1 up to Q4, where all of the QI's are primes, except possibly one, which might be a product of two primes. So we can't rule out that possibility. So there we are, Heath-Brown's result. And, well, what I'm here to talk about is a recent preprint of myself and Terence Tao, which purports to prove that there are arbitrarily long arithmetic progressions of primes. So from 3.5 to k, as it were. So a feature of this subject of sort of additive prime number theory is that really none of these facts are at all surprising. I mean, I think people would be inordinately surprised, well, you know, maybe 68 is not the sum of 2 primes, although actually it is. But there may be, people would be inordinately surprised if it wasn't the case that every large even n is the sum of 2 primes. And the reason being that if you take a large even n and just subtract some prime from it, there are sort of a vast number of primes that you might subtract from it, basically n over log n of those by the prime number theorem. And the chances are that for one of those, you're going to match up with another prime on the right-hand side. I mean, it would be just amazing if you missed all of those. But that doesn't constitute a rigorous proof, obviously. In fact, much the same argument would serve to show that there are infinitely many primes that differ by 1. So that shows you that it has to be bogus. Anyway, however, somewhat more sophisticated arguments along this sort of heuristic will sort of make you believe that there really should be huge numbers of arithmetic progressions of primes, huge numbers of representations of an even number as a sum of 2 primes, and so on. So none of this is surprising. The difficult thing in this subject is actually proving that things work. So how do I, is this on? Lamp?
I think lamp is the thing to do. And also this one we probably should put on.
Oh. I think that's probably working. Right, so I can summarize, well, one major aspect of this work is that we don't really understand anything new about the primes other than the statement that there are arbitrarily long progressions. What we've succeeded in understanding is a bit more about arithmetic progressions, the structure themselves. So the study of arithmetic progressions from the abstract point of view, from the combinatorial point of view, was initiated much more recently by Erdős and Turan. And they asked basically this question. Is the reason, I mean, we suspect the primes contain long arithmetic progressions. Is that just because there are lots of primes? So let's take a set A contained in the interval 1 up to n. And Erdős and Turan asked, how big does A have to be before you're just guaranteed that A contains a k-term progression? So define R sub k of n to be the size of the largest set A which doesn't contain a k-term progression. So the size of the largest set not containing a k-term AP. And the content of their paper was more or less just the question, what is Rk of n? And that's been a very good question, it turns out. So I guess if you're thinking about primes, it's natural to ask, is Rk of n less than n over log n, or sort of n over 2 log n? Because if it was, that would mean that the primes automatically contain k-term progressions. So there's a somewhat less optimistic question. Can we even show that this is a quantity that grows more slowly than any positive multiple of n? That alone has proved to be a very, very difficult issue. And it was only 17 years later that Klaus Roth obtained the first serious result on this, when he proved that fact for three-term progressions. So if A is a subset of 1 up to n, with size n over 500,000, then provided n is sufficiently large, you get 3 elements in arithmetic progression. And actually he obtained this quantitative bound here, n over log n. That doesn't tell you anything about primes because log is much, much smaller than log. And then a while later, Szemerédi confirmed that question in the case k equals 4. So he proved R4 of n is little o of n. And then he sat down for a further 6 years and knocked out the general case. It's a ridiculously difficult paper which very few people claim to have read. although Terry read it recently, actually. So I'm pretty sure it's right. Now, that's not the end of the story. So the theorem is proved in full generality. But since then, people have invented various different ways of proving it, some of which give more information, well, all of which give more information. So it was a great achievement of Furstenberg in 1977 to provide a proof of this statement, Rk of n is little o of n, using ergodic theory. So the frustrating thing about Furstenberg's argument's beautiful, but there's a frustrating thing about it, and really about Szemerédi's original argument, which is it gives you no bound whatsoever on these quantities. So although Roth's argument gives you a statement of this sort, these arguments of Szemerédi and of Furstenberg basically don't give you anything here. They just tell you there exists some function which tends to zero very slowly. And then my thesis advisor, Tim Garrett, obtained what I call the first sensible bound. That's definitely sensible in this sphere of study, which is log log to a power. So we know Rk of n is bounded above by n over log log n to a power. What we'd like to know, for a start, is it bounded above by n over log n? That would do the primes. And the best known lower bound is sort of ridiculously different to either of these. It's basically, that's n over e to a constant root log n. So it might well be true that the primes contain progressions on density grounds alone, but nobody knows how to prove it. The upper and lower bounds are still out by, let's say, a double exponential. And that isn't an issue that we've been able to address either. So the strategy that we use is to prove what we call a relative Szemerédi theorem. Here's Szemerédi's theorem. So we have the integers, or the set 1 up to n. And the setup is that we have a positive density subset of it. So let's just say size at least n over 1,000 for the sake of argument. And the conclusion is that A contains long arithmetic progressions. But let's not be too ambitious. Let's start off with 4-term progressions. So A has 4-term APs. So we're going to create a sort of analogous theory on the left-hand side of this, in which the conclusion is that the primes have 4-term progressions, which wasn't known before. So here, we're going to exhibit the primes as a positive density subset of something. So we're going to find something up there such that the primes are contained in something with positive density. So I can now reveal this slide, which just says exactly that. There it is. Oh, and it says slightly more, that the mystery object is, well, it's kind of a function, a non-negative function, supported on this interval 1 up to n. So what is this mystery function? Well, there came a time when I was looking for mystery functions like this, and the first thing that we tried was to take, instead of the primes, to consider sitting above the primes the set of all things with at most, let's say, 1,000 prime factors. Turns out that the primes are a sort of largish subset of that. But unfortunately, we couldn't work with that. And I went to visit Andrew Granville in Montreal, and I basically asked him what functions he knew that the primes lived inside, and this is what he said. Well, actually, I'm jumping a step ahead. Let me tell you in more detail what I said to Andrew Granville. I said, I need a function nu which has the following properties. And these are the properties that Terry and I couldn't make work with the numbers which have at most 1,000 prime factors. So if we're dealing with 4-term progressions, this function nu must be non-negative everywhere. The primes must sort of sit inside it. So if n less than n is prime, then nu of n is at least 1. That's a suitable definition of sitting inside nu. Then the primes have got to have positive density in this function, and a sensible definition of that is that the following holds. For the sake of argument, the total weight of this function is no more than 1,000 times the number of primes less than n, which by the prime number theorem is n over log n. So far, nothing too deep. It's pretty easy to come up with a function that satisfies these properties. For example, the characteristic function of the primes themselves will do that. But it's the third property that was what really challenged us. So nu must satisfy the correlation condition. Let me not bother to actually write that out, seeing as it's all written here. There it is. So we need to be able to evaluate expressions of this sort. So this is 32 here is a function of 4, if you like, which is the length of arithmetic progression we're thinking about at the moment. Now let's just look at this expression. If we could find an asymptotic for this when nu is just the characteristic function of the primes, h1 is 0, and all the rest of the hi's are equal to 2, that would give us the twin prime conjecture with a sharp asymptotic. So that's not going to work with just nu being the primes themselves. So we really do have to sort of find something that's genuinely bigger. And here is what it is. Interestingly, it came to us via Andrew Granville from work of Dan Goldston and Cem Yildirim on gaps between prime numbers. And they considered this function here. That function, I mean, they weren't really the first people to think about that function. It comes from sieve theory, and Selberg had thought about this in various contexts. So what is that function? So r is a small power of n, and then we have this thing 1 over log r squared times the sum over the divisors of n less than r, mu of d log r over d squared. Mu is the Möbius function, so just in case anyone's not familiar with it, if you have a product of distinct primes, then Möbius of that product of distinct primes is minus 1 to the number of those primes. If n has a square divisor, then Möbius is 0. And the only remaining case, which is actually the only one that I'm going to use in a moment, is mu of 1, which is 1. So this is the function. Well, that's the function nu if n is bigger than r, which almost all n are. So let's look at what happens if n is a prime. Then you have this sum over the divisors of n, and if n's prime, there are only two divisors of n. That's 1 and n. And the only one that comes into this is 1, because n is bigger than r. And so the sum just totally collapses into mu of 1 times log of r, And so you just get 1. And so this function really does dominate the primes. What Golson and Yildirim did for us was verify this correlation condition. So they found an asymptotic for things like this. And, well, I'm not going to say anything about how they did that, but there's nothing too mysterious about it. It's classical analytic number theory using a zero-free region for the zeta function, much like you would do to prove the prime number theorem. Okay. So we have this function nu, which dominates the primes, and it's lying around, and it's going to be helpful. But for now, let us go back to arithmetic progressions. So how can I count arithmetic progressions in various types of set? Well, let's just ask a basic question. So let's just take a set, and let's fix the size of that set. How many 3-term arithmetic progressions does this set contain? Well, the question is somewhat analogous to asking how long a piece of string is. I mean, it depends on the set A. Well, or does it? So let's think of some examples of sets A like this. As a combinatorialist, one of my favorite examples is the random set of size alpha n. And to generate a random set, you just take each element 1 up to n in turn with probability alpha and choose it independently to lie in your set A. So how many 3-term APs does that have? Well, for every potential 3-term AP, which has that form, you want all 3 of its elements to lie in, and so you've got a probability alpha, 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 so that's alpha cubed. How many of these objects are there? Well, basically there are n choices for x, and then sort of another n choices for d, although if you were unlucky, this might lead you to going outside this interval. So it turns out that it's a quarter of that number. So a random subset of 1 up to n, density alpha, is going to contain about that many 3-term arithmetic progressions. But that's just random sets. So what if you, I mean, does every set behave like a random set? So there we are. There's the question. And yeah, so in the random case, we have about that many 3-term APs, and I'm going to call that the expected number of 3-term APs, because most sets are kind of random. But some sets aren't random, and here's one example. Let's just take the initial segment consisting of the numbers 1 up to alpha n. And this contains many, many more 3-term APs than a random set. And it has about a quarter alpha squared n squared 3-term APs. So something's gone wrong. But that's a very, very special type of set. I mean, we've gone from the sublime to the ridiculous. This is a completely structured set. And a very important fact for us, which you can prove using harmonic analysis, is that in some vague sense, this is really the only type of set which doesn't have nearly the expected number of 3-term progressions. And this is what you can prove. If A is a subset of 1 up to n with size alpha n, it doesn't contain roughly a quarter alpha cubed n squared 3-term progressions, then that fact is explained by A having linear bias. And that means basically that the characteristic function of A has a large Fourier coefficient. And I can draw this pictorial as follows. Here is sort of 1 up to n, if you like, drawn round in a circle to make it into a group. And here's that very structured set A that I just took, 1 up to alpha n. And what you're doing when you're considering linear bias is you're weighting the characteristic function of A by a Fourier exponential. So in this instance, I'm going to weight it by e to the 2 pi I over n over n. So that corresponds to taking theta equals little n over big N here. And what happens is that you basically end up taking this sum of exponentials. And as you can see, you're not going to get any cancellation there because they all point in basically the same direction. So a natural question at this point is, well, let me think what my next question was. There are two natural questions at this point. Oh, yes. The first natural question is, what about the primes? So when you're dealing with the primes, it's convenient to normalize them by considering instead the von Mongolt function. So that's basically just the primes up to n multiplied through by log n. Not quite that, but basically. And if you do that, then you have a function with average size 1. And it turns out that you can show that either the primes have the expected number of 3-term progressions, which is this thing. So here we sort of normalize things so that the primes behave a bit like a set of density 1, if that makes any sense. So either they, I mean, if this were the case, then we'd be happy if we're trying to prove that the primes contain lots of 3-term progressions, because n squared is huge. So either that's the case, or the primes have linear bias, which is given to us by, well, it's basically the statement up there, but with the primes in place. Now there's a subtlety here, because what I didn't tell you was quite how we prove that if A doesn't have the expected number of 3-term APs, then it has linear bias. It used some harmonic analysis, and if you just try and do that with the primes, you end up losing a factor of log n. So instead of that c, you'd get sort of c over log n. And that's going to be a problem for you, it turns out. And so to prove the strongest statement there, you've got to have that function nu that I carefully constructed, this function of Goldstone and Yildirim, kind of lying around. I won't say quite how it lying around helps you prove that, but trust me, it does. So there we are. Either the primes contain lots of 3-term APs, or they have linear bias. So all we need to do is show that the primes don't have linear bias. But that's false, sadly. So, well, because basically all primes are odd, they have a rather strong linear bias in one direction. So if you take the primes, or the weighted primes, and weight them by the exponential e to the pi I n, since almost all primes are odd, this is almost always going to be -1, and so you don't get much cancellation when you take this sum. So that's bad. But there's a trick which we call the W trick, which sort of means that you can think of the primes as though they didn't actually have these sort of nasty linear biases. So if you, okay, so all primes are basically odd, but what if you just look at how the primes look along the odd numbers? So just sort of delete the even numbers and then rescale the odd numbers so that they look like everything. Then you don't have this parity problem anymore, because there are infinitely many primes, or equal numbers of primes of the form 4k plus 1 and of the form 4k plus 3. And okay, this just explains in general how we sort of rescale the primes to delete these small arithmetic biases. So I'm going to replace the primes by a sort of rescaled and arithmetically smoothed out version of them, lambda tilde. And then the statement I claimed over here remains true. Either lambda tilde has about the right number of 3-term progressions, or lambda tilde has linear bias. Two pi I n theta. And at this point, you can appeal to the ideas of Hardy and of Littlewood, which tell you that this second alternative doesn't hold. So actually, the primes do have lots of 3-term arithmetic progressions. Right. So that was the first natural question. How does this business of not having the right number of 3-term progressions relating to linear bias transfer to the primes? So it basically does transfer to the primes. The second and much more interesting question, I think, is how does it transfer to progressions of length 4 and longer? So let's consider this random example again. Pick a random subset of 1 up to n by picking elements with probability alpha. Then, by much the same argument, chucking in an x plus 3d here, you can calculate that the expected number of 4-term progressions is basically 1/6 alpha to the 4 n squared. Is it, so once again, there are examples of sets which don't have nearly this expected number of progressions. One example would be the set I had before, the initial segment. So that certainly messes things up, but maybe it's still true that if you don't have nearly the expected number of 4-term progressions, you still have linear bias. Unfortunately, that isn't true either. So consider the following interesting looking set. So it's the set of all n less than capital N, for which the fractional part of n squared root 2 lies between, well, minus alpha over 2 and alpha over 2. So it turns out, not obvious, that this is a set of size approximately alpha n. It turns out that it also doesn't have linear bias, so it doesn't look even remotely like one of these highly structured sets. But the unfortunate thing, if you were just trying to naively generalize what Hardy and Littlewood did, is that this set doesn't have even remotely close to the expected number of 4-term progressions. And I shall reveal why that is in just a moment. So there's all those questions. Why does it have the wrong number of 4-term progressions? Well, it's just due to a very simple algebraic identity, which the bored listener can verify, which is x squared minus 3x plus d squared plus 3x plus 2d squared minus x plus 3d squared is equal to 0. Nothing too controversial there. But the thing is that if x, x plus d, and x plus 2d all lie in this set A, then x plus 3d is constrained. So if you multiply this through by root 2 and just work out what happens, you get that if x, x plus d, and x plus 2d are all in A, then the fractional part of root 2 times x plus 3d squared, well, it lies with it in the interval minus 7 alpha over 2 up to 7 alpha over 2. And in particular, that means that x plus 3d is much more likely to lie in A than it should be. So it's not independent of x, x plus d, and x plus 2d lying in A. Right. So, in my opinion, somewhat remarkably, these are essentially the only obstructions to a set A having about the right number of 4-term arithmetic progressions, or nearly the expected number. So in other words, there's a theorem that's directly analogous to that theorem for linear bias. And it says, suppose that A has size alpha n, and that it really doesn't have about 1/6 alpha to the 4n squared 4-term progressions. Then it has quadratic bias, which just means, well, it looks almost exactly the same as the definition of linear bias, except that theta times n, my linear function, has been replaced by what I call a generalized quadratic. So let me just before I say what a generalized quadratic is, let me explain the somewhat interesting attribution of this theorem. So it's sort of, in this form, it's really due to Gower's plus one extra idea of myself and Terry. The reason Host and Krah are there is that an analogous statement to this has been found in the context of ergodic theory. As always with ergodic theory, you don't get any bounds for this function f, but purely qualitatively, this has also been shown by Host and Krah. Anyway, so what's a generalized quadratic? Well, I'm not going to tell you, but I will tell you some examples. So linear functions are considered generalized quadratics. So are functions like n squared root 2. And then so are some rather unfortunate functions, like n root 2 times the integer part of n root 3, or sort of root 2 times the integer part of n root 3 times the integer part of n root 5. Those are funny functions, and people aren't really used to dealing with those. So there they are. So this begs the question, given what we did for progressions of length 3, if I take the von Mongot function, which is quadratically biased because most primes are odd, but then I quotient out by this arithmetic nonsense to get lambda tilde, can I show that that function doesn't have quadratic bias? It turns out that if I could, then I would get lots of four-term progressions of primes by an argument which I haven't really told you, but which involves that function nu that I constructed earlier. Unfortunately, well, the answer to this question has been basically no until recently, and now I think Terry and I can show that the modified von Mongot function doesn't have quadratic bias. But that's certainly not how we did things originally, and it's going to be a long and probably somewhat unreadable paper. So seemingly yes. Oh, and if we indeed have shown that, it's going to give us an asymptotic for the number of four-term progressions of primes, all of which are less than n. And also for kind of non-homogeneous systems of two linear equations, I suppose things like p1 plus p2 plus p3 equals n, and p2 plus p3 plus p4 equals n dashed. I haven't really thought about that, so if it's trivial by other reasons, then whatever. But what we did in our original work is find a way around the problem of showing that, of trying to prove that the primes don't have quadratic bias. And it's phrased in the form of an algorithm. So there's the start of the algorithm. So I took the sort of arithmetically modified primes, and I wrote them as 1. I wrote them as 1 plus an error. And I know, well, what I'd like to show is that this f naught doesn't correlate with a quadratic function. So it would be nice if I could show that this is small, say little o of n, for all q. But as I said, we didn't really know how to do that. So maybe there is such a q. Maybe there is a q for which this sum is large. And if there is, then we're just forced to admit that there is. And we modify the function 1 using it. So I'm going to modify well, actually what I do is I take my putative e to the 2 pi I q and sort of decompose into approximate level sets of that function. But that doesn't really matter for what I'm about to say. So I get a sort of new decomposition of the von Mongot function as an f1 plus a little f1. And it's not too dissimilar to what I started with. So the new f1 is bounded, it turns out. It's basically less than 100 everywhere, bigger than 0. And that's yet another instance of using this dominating function nu, which we've had lying around for the whole argument. So let me say existence of nu implies that f is basically a bounded function. So when I've done this decomposition, I'm going to ask the same question again. Does f1 correlate with a quadratic? And if it doesn't, then I'll stop. And if it does, then I'm just going to modify f1 in a way that I'm not quite going to tell you to give a new function f2 plus another error. So there's the first stage of the that's just writing the first stage of the algorithm. Modify 1 to get f1, and then I repeat. So it turns out that all of the FIs that I construct are basically all dominated by 100. Now, an algorithm is generally not too much good unless you have a way of finishing it. And thankfully we do. So theorem, the algorithm terminates. Roughly speaking, the reason for that is that it turns out that the L2 norm of these functions, fi, the way the algorithm's done is that the L2 norm of these functions just increases at each step. But it can't because they're all just dominated absolutely by 100. So if it increases by a fixed amount at each step, yet it's bounded by 100, the algorithm has to stop. So let me just write L2 norm. And so when it does stop, what you've done is decompose the primes in this way, where this is a function with no quadratic bias, or very little quadratic bias. And that is a function which is basically bounded by 100 everywhere. So, yes, that's what happens when the algorithm stops. And when it does stop, we sit down and write out this expression, which is basically the number of four-term progressions of primes, or modified primes. And it clearly expands into a sum of 16 terms. Now, for 15 of those terms, there will be some involvement of this little fk. And basically, the fact that this doesn't have any quadratic bias means that you can basically just forget about those terms. So there's really only one term left, which is this. And this fk is a function dominated by 100 and with average value 1. And so sort of morally speaking, it resembles a set of density 1% or something like that. So there's the other term. And we can think of it as being a bit like a subset of 1 up to n with density about 1 over 100. And so just chuck Szemerédi's theorem at it, and that will tell you that this function fk, or that this expression 1, which I didn't LaTeX enough times, is going to be large. So we've just thrown Szemerédi's theorem as a black box at this problem and got something out of it. The theorem we get out of it is that the expression at the top here, being more or less equal to expression number 1, is large. And in particular, the primes contain lots of four-term arithmetic progressions. Now, Peter Sarnat remarked to us that the only reason we succeed here, really, is that we're proving a much stronger statement, or a seemingly stronger statement, that in fact any positive density subset of the primes also contains a four-term AP. In fact, you move up to progressions of length 5. So progressions of length 3, linear bias was the thing that was being dealt with. Progressions of length 4, it's quadratic bias. So no prizes for guessing that for progressions of length 5, there's going to be some notion of cubic bias. But just as it wasn't the case that quadratic bias was all about absolute, genuine quadratics, for cubic bias we have to deal with these really unpleasant-looking things like this. And at the moment, we don't really know how to deal with those. So what we actually do is replace these linear, quadratic, and cubic functions by things which don't look at all like them, but kind of act as if they were them. So I'm not going to be in a position to really explain that too much, other than to show you what these things look like. So that's a surrogate linear function. It's basically a triple convolution of basically just any function with itself. And a surrogate quadratic function is, well, it's sort of like a, I guess you'd call that a quadratic convolution. It's a sum over 7 vertices of a 3-dimensional cube of values of a function f. So as I say, it sort of turns out that morally, these funny sums are basically, or can be thought of as much the same as e to the 2 pi I root 2 n squared, or something like that. And this generalizes very easily. So a linear function is a sum over 3 sides of a square, 3 vertices of a square. A quadratic function is a sum over 7 vertices of a cube. Cubic function is going to be the sum over 15 vertices of a 4-dimensional hypercube. So it does all generalize to k-term progressions. And then, so here are some future directions in this whole theory. As I said, we now think that we can show that the primes don't have quadratic bias. That would be quite nice, because it would tell us an asymptotic for the number of 4-term progressions of primes all less than n. Can we generalize this to cubic and so on biases? Well, it's sort of more or less clear how such a theory is going to have to go. And we want to do it. Hopefully we're going to do it. But it's not going to be too easy. I mean, for a start, we're going to have to read Tim Gower's 129-page paper on Szemerédi's theorem. And that'll just be the warm-up. Then we have to do basically everything that we found already quite hard for 4-term progressions in this more general context. And here's just a sort of idle speculation. So our methods will also allow you to deal with arithmetic progressions of sums of 2 squares. Actually, it's a sort of 5-minute exercise to show that there are infinitely many 4-term progressions of sums of 2 squares. You can just write down a parametrization. But to get an asymptotic is more difficult. And observing that that amounts to counting integer points on a certain variety, which is an intersection of 2 quadratic forms in 8 variables, I sort of wonder whether we might be able to address that kind of question, counting points on varieties, in somewhat more generality. So that's all I'd like to say. Thanks for listening.
Any questions? Then let me ask one which probably shows my ignorance, which is there any hope of attacking the twin primes?
Twin primes conjecture is going to be tough, actually, because the problem with the twin prime conjecture and this approach is that if you have a set which doesn't contain any solutions to y minus x equals 2, then it need not have linear bias, certainly, and in fact it need not have quadratic, cubic, or anything bias. In fact, a more or less random-looking set can have the property that no 2 elements differ by 2. That's going to be a big issue. So I think basically the answer is there's no hope whatsoever of proving the twin prime conjecture or the Goldbach conjecture in this way.
Any other questions?
So you prove that there are infinitely many 4-term progressions of what was defined.
Yeah, we proved that.
So for any n, there are infinitely many.
Yes, yes.
Well, let's thank the speaker again. Oh, sorry, another question?
Just had a question. Do the arithmetic progressions have like any application to like factorizing large numbers?
I guess no. I mean, so let me slightly reinterpret your question as maybe you're saying something like, can we pin down these arithmetic progressions in any way? And the answer, I know that wasn't actually your question, but the answer to that is no. I mean, these things, all we know is that these things exist, and we know almost nothing more than that. We do actually get a bound on where they lie, but the bound is utterly ridiculous. So if you want to find a k-term progression of primes, it suffices to look up as far as 2 to the 2 to the 2 to the 100k, where that tower has height 7. So I think it's fairly safe to say that there are no applications to computation that are going to come straight out of this.
Let's thank the speaker again.